Alors, juste 2 mots sur Jens Meunig, qui a une particularité, c'est qu'il en a au moins 2, c'est qu'il est à la fois avocat et programmeur de haut niveau. C'est lui qui est à l'origine du langage Snap, dont il va nous parler, qui a été fait avec l'université de Berkeley. Donc voilà, le temps qu'il s'installe.
Okay, great.
Voilà, je lui laisse la parole. À toi.
Merci Didier. Bonjour, good morning. It's been a great conference for me yesterday, listening to all your presentations, and it's been remarkable in many ways. One way that really struck me as being remarkable was being at a conference where I saw lots of blocks-based environments. I saw lots of Snap, saw lots of Scratch, some Blockly, but I also saw quite a few textual languages, Python, JavaScript, and others. But I didn't hear any presenter asking the question, like, how do we move on from transitioning kids from blocks-based programming to text-based programming? Probably you've all been talking about this in French and I didn't understand any, but I just wanted to say this is something I find remarkable in a very good way. It seems that you're very comfortable kind of exploring both modalities of programming. So, my name is Jens Meunig. I'm a researcher with SAP and HARC at Y Combinator Research, and I'm the lead developer of the Snap programming language together with my friend from Berkeley, Brian Harvey. And sometime yesterday I noticed that probably everybody already knows about Snap, and I felt like, geez, I'm coming to the wrong conference. I'm preaching to the choir. Everybody knows. So just very quickly, Snap is the language that has been created for UC Berkeley's new introductory computer science course for non-majors, which is aimed to broad participation by underrepresented minorities. It's directed at interesting history majors and English majors in the big ideas of computer science. The curriculum has been developed at first by UC Berkeley, and now since 2 years there's more curriculum development by the Education Development Company in Waltham near Boston. And for this curriculum that is called The Beauty and Joy of Computing, which is also a pilot of the new Advanced Placement Computer Science Principles Framework that is being installed nationwide right now. And just a few weeks ago, the Beauty and Joy of Computing curriculum has been officially endorsed by the US College Board. There's also an edX MOOC online and a grant from the National Science Foundation to bring BJC and the Snap to every high school in New York City, which is the largest school district in the US. Technically, Snap is a browser-based IDE. It's pure JavaScript with some HTML5 APIs, mostly Canvas. So no plugins required, and this was important to get it into schools because you don't have to deal with school IT and to get something installed, which is often very hard. It's been translated into 38 languages, including French. It's free, not just free as a beer, but free as in you can download the source, you can fork it, you can make it your own, and there are numerous people who've made their own forks of Snap. There's also a cloud backend where you can upload your projects, which is not just useful as web storage, but for example, if you're starting out on one computer in school with your project and then would like to continue at home, or you're starting at a PC and you'd like to continue on an iPad or something. And so what about Snap? My co-author, friend Brian Harvey, likes to say that Snap basically just looks like Scratch, but it is Scheme at heart. And what do we mean with that is we're taking from Scratch the looks and the feel. So we're taking the micro world, the stage, the sprites, and making it pretty much look exactly like Scratch. That's the idea. We're having costumes, we're having sounds, we're having the blocks looking the same, clicking together. We have events, we have which I think is one of the main things Scratch brings to the table, the ubiquitous parallelism, that whenever you broadcast something, even without knowing about it, you start delving into parallelism, which is quite remarkable if you think about other beginners programming languages. And the last thing that personally I find very, very great about Scratch is that it's always live. You can click on a block of the palette, you can click on a block in the scripting area. It is live medium. There is no compiling, run cycle. You can plan ahead if you want to, but you're not required to plan ahead. And this kind of continuous feedback is very good, for self-learners, and it's also something that really enters you into learning. So this design by Mitchell Resnick and by the Scratch team of MIT is really brilliant in that it really has been cool with kids even before teachers discovered it. And we wanted to retain this, to have the low floor, as Mitch likes to say, to really get people into programming, not scare them away. So the stuff we were inspired to take from Scheme is more the computer sciencey things. So to enable to use Snap for a full semester of a technically rigorous introductory computer science course and not have to switch languages after 2 weeks when students can no longer switch subjects. So we added things to enable this computer science course, and it's basically dynamically typing the variables, having lexical scope, adding a bunch of first-class things, including first-class lists and lists of lists, which let you build arbitrary data structures, adding blocks, the idea of blocks as data, which lets you build arbitrary control structures and enhance the language. And we even added first-class continuations, more as a joke originally, but turned out they're useful. You can build your own catch throw blocks. And also from Scheme we took proper tail recursion, which we wanted so you can build your own loops without running out of memory, right? Without causing a stack overflow. So you're free to explore not just, as Vasily I think said yesterday, the imperative paradigm, but also the functional paradigm, which is the rally cry of Logo, no ceiling. And there's some things we kind of were inspired to take from other languages as well, like Smalltalk and Self and Logo. Some things like sprites can be nested, so you can build a virtual robot and check it out. We've got a way to display tables. We can access web APIs, and that's actually how Poppy is controlled, as I understand it. We can extend it with JavaScript, basically turn JavaScript into new quasi-primitives, and there's also other features, so we can transpile it to other textual languages to see that the blocks really is kind of the more general way to represent code and programs. And this all leads up to wider walls. There's a bigger variety of ways to solve a particular project and a bigger variety of apps you can make with Snap. So, let me show you. And this is the part I'm a little unsure about because you probably have all seen this, right? Has anybody seen this already? Am I kind of boring you to death? Okay. Be brave. Nobody's brave. Okay, I'm gonna, okay, good. You're in. So this is the project that started all of Snap, really. It was pretty much 8 years ago at the first Scratch conference when Brian Harvey, at the last day, had a session, and we had just put lists into Scratch, and we were really proud of what you could do with lists, and you could broadcast, things that are in lists and which are basically text. And he had this example, which is from another friend, Paul Goldenberg, also an old Logo person, of things you cannot do. So what you see here is this stage with a list watcher, and in this list watcher is a bunch of blocks. Every Scratch kid immediately gets this. It's a list of blocks. And so here's a little program, and it has a bunch of custom blocks. Here's how we define a square. It draws a square, just repeat 4, kind of move the old turtle geometry thing. And we have a function called v, which is basically an abbreviated tree. It turns left, go back, turn right, go and go back. But at the end of every path, run something arbitrary from that list. And in the list we have the blocks. So if I run this program, I get turn left, and in this case it's a square, turn right, in this case it's a star. If I press it again, I get something different, or maybe not. The interesting thing happens if I add things to that list. So here, heuristics have shown that adding twice v kind of leads to more beautiful things. So now I'm having a list, and we usually start asking questions like, what do you think happens? What do you think can happen? And so, what do you think happens? Anybody? Excuse me? It goes on forever? It's a snowflake. Could be. Should we just try it? Let's try it. Kind of. So we see at the end, it can be another V, and it can fork. And usually it fizzles out. It's a mathematical probability that it will not go on forever. But we sort of get these random shapes, and you're right about the snowflake. It's a fractal, right? Because, and it's a nice thing. So with this example, we introduce both recursion, and the nice thing is it's recursion without a base case. The base case is just a probability. But we also introduce a list of procedures. The idea of procedures data, which is traditionally considered to be a hard idea for computer science education, especially for non-majors and for kids. But the thing is, Scratch, having this beautiful design of blocks and lists, it's kind of immediately clear. It's a visualization of what goes on. Let me try. Sometimes it goes really wild. Ah, look at that. Yeah, sometimes when you're lucky. Okay. So just to expound a little bit on this idea, here's the plus block. And the usual thing you try is you put some numbers in and you click on it and you get the immediate feedback, which is just great. I hate these languages where you have to compile these things first, upload them to a computer, to a robot even. The robot then determines what 3 plus 4 is, sends it back to your computer, and it somehow outputs to some standard output. That's just not how computing should be in the 21st century. So you click on it, you get the result. But there's also this thing. This is a ring, and if I put this function into the ring, what I get is the block. And this is basically a reification of the block. It's a lambda, and then I can call this again, and I'm getting the 7 again. And what seems like really trivial can lead to quite interesting things. So I can also leave this empty and put in a 5, and what do you think I'm getting? Okay. Somebody knows? What if I click here? What do I get? Nobody? Maybe it's not obvious. We're having a, who said something? 10? Yeah, I'm getting 10 because the input is sort of mapped to both the empty spaces. This is an idea we took from the new math movement, I think back in the 70s, and we're currently having a design discussion whether it's actually a great idea or not. Because now we could also, what do I get now? Yay. Okay. This is quite boring. It gets more interesting when we use it as a higher order function. So the simple example of a list, this is really kind of boring, but nonetheless, it'll get interesting in a minute. So I have this list, and I map this block over it. And now just gives me a new list with the +2 function applied to every instance of that list. And that is actually a pretty powerful idea. That is actually something that is beyond of what many beginners programming languages can do or even represent, and especially since this block is made in Snap itself. So you can write your own higher order functions, your own blocks that do these kinds of things. And I mean, this is just very general. We can relabel this to the ×2 function. I'm getting the double, or we can do it like this. And now we're having a square function. And we can be fancy and do it like this. Then we're getting a list of lists. And to be even more fancy, what do you think we're getting now? Now we're getting a table, which is basically a visualization of a list of lists, and in the first column there is the number as it is in the list, and in the second column there is the square. And this is really just a new visualization for what used to be a list of lists, but for the special case that is two-dimensional, we represent it now by default as a table view. So let me show you an example of the power of this kind of thinking in higher order functions. Oh wait, that's the wrong one. Here's a picture. The building might seem familiar to you. I took last night from, I think it was over there, from this building here. And in this project, I have a block that gives me the current costume, and I've got a block that gives me the pixels of the current costume. And so if I evaluate the pixels, what I'm getting is a table, which we just heard is a list of lists. It has 90,000 rows and 4 columns, and it's easy to guess that the 4 columns are the RGBA values, and that each row represents 1 pixel. So, wow, it's just data. It's just a list. So I wonder what happens if I do something funny with that list. Let's say for every pixel I'd like to reorder some things, which I do. I make a function that returns another list, and in it, let's say the last, I want to stay the last, which is the alpha value. And the first one should actually be the second. And the second one should be the third. Let's put this back. And the third one should be the first. So now if I evaluate this, it takes a little time for Snap, which isn't the most powerful language of the world, to iterate over 90,000 rows, but here they are. So now I can compare them. Left is the original list, right is the modified one. So in the original, I have kind of in the first value, we've got 9, 14, 18 has been switched to 14, 18, 9, sort of switched around. So let's check this out. This is an example, by the way, that Mark Guzda likes to do with his students in his media computation course, and I've sort of stolen this example from him and made it, adapted it to this functional way. So what do you think happens to Bordeaux's blue sky if I press this? Oh, already there. The colored channels have switched. And this is an interesting thing, how we can use higher order functions over just regular data, make a graphic effect, make your own graphic effect. It's fun to use this also on sprites. And wow, you can even click on it again, since it's kind of arranged in a way that it's lossless, it didn't change anything. So the house kind of stayed the same. Now the sky is really dramatic, and the grass is somewhat bluish. And if I click on it again, I think I should be getting back to normal. Yes, I am. So this is an example, one example for the power of higher order functions. I'll give you one more example, and then I'm already done. And I might be boring you with this, but I'm just so proud of this, I need to show this off. So, Scratch doesn't have many of the control structures that other programming languages have. For example, one glaring omission that people often find limiting is it doesn't have a while block. Like every language has to have a while block. There is none in Scratch. So with all that I've shown you just now, let's just make a while block. It's going to be in the control category. I'm going to call it while. It's going to have a test and an action. And I need to make a special case here. A special form means that it doesn't get evaluated before it gets passed into the block, but it gets passed into the block unevaluated, and we have a choice for that. So the Boolean is going to be unevaluated. And the action is also going to be something that is going to be evaluated or not. So it's also going to be unevaluated. It's going to be a C-shaped block. So now I have the block. It already looks like it should look. I'm just going to make a stupid thing, a stupid example. A variable which I'm going to initialize with 1. It's going to be, changed by 1. I also want to say it for a second, and while it is lesser than 5. Excuse me? I need to. Thank you. So this is what it should do right now. It doesn't do anything because it's not defined yet. I can define this in Snap by using an if block. And now what I'm getting is an unevaluated thing which shows a lambda. And I've shown you before that to evaluate it, I just call it. So if this evaluates to true, I can run the action, and then I need to repeat doing it, which I can do recursively by just kind of doing the same thing over, putting the action in here recursively. This is the definition for the while block. Check it out. It's not working. What did I do wrong? Test run action. Jeez. Excuse me? Oh, okay. My God. Of course it's not working. Thank you. This is 0. And it goes up to 4. And stop, and the variable keeps incrementing because it keeps incrementing. So this is an example of how you can change the language, how you can enhance the language with control structures that it doesn't have. And try this in Java. It's not going to be easy. Now with Java 7, you might be able to do something like that, but this is definitely a concept that is quite not what is usually expected from a beginner's course. And this is what we're talking about when we're talking about blocks for real and no ceiling. Questions? Thank you. Yeah.
Ouais, tiens, Mathieu a un micro de l'autre côté. Ah bah attends, non c'est bon.
Thanks a lot, Jens, for this wonderful talk. So I'd like to have a question on your last sentence, about educating students to like lambdas and having no ceiling. In your experience, at what level can we teach students those concepts? And because it seems to me that indeed Snap is a great tool to teach those concepts, but maybe not so much to the youngest. Maybe I think the use of Snap at the university level is great for this. But then, in terms of no ceiling, typically in terms of expressive powers, there is no ceiling. But then those students that are going to get into the lambdas, those ones probably they want to make their own apps they can share with their friends, like native apps. So, what would you say about that?
Good questions, Pierre. Actually, I'm not a teacher myself, but you know, this is a matter of debate. I can tell you that some people, especially my friend Brian Harvey, feel very enthusiastic about making concepts such as Lambda and functional programming accessible to even young kids, and saying, you know, there is actually this idea isn't so hard once you have a visualization for it. It's just that it's been considered hard for probably all the wrong reasons. But mostly everybody else agrees it's a pretty advanced concept that might, you know, scare people off. So one way to introduce it that we're doing is that we're letting them use higher order functions rather than build them themselves. So we're giving them map, we're giving them reduce and filter, and then they can explore this on lists. And this is usually found to be really easy. And then it's nice, you can let them see how it's actually made. And you know, to be honest, building higher order functions yourself isn't even required in the AP CSP course. It's something that the Beauty and Joy of Computing adds sort of as something to something special to their students. Yeah, sharing as an app is also a good question. There is actually somebody, a guy from Spain, Adrian, who made a website which actually lets you lets you package a Snap application as a standalone application for either Windows or Mac OS. That's quite cool. And of course, there might be other things in the future that also package that.
So I have a question. So thanks again for really inspiring talk. Is this on? So this microphone on. I have a two-part question. The first part you don't have to answer because the elephant in the room is Scratch's advantage of the ecosystem that encourages the sharing economy between young programmers, and that's something that's not necessarily a question that needs to be answered by the programming language, but by the author. But the question is consequently, because programmers want to share their code, what subset of Snap is transpilable into Scratch so that they could then share their programs in Scratch? Maybe not a beautiful Scratch program, but a functional Scratch program.
Awesome subject. There's actually, we have hijacked 2 threads in the Scratch forums, and there has been a discussion for weeks of how to transpile these things into low-level subset of basically push and pops on Scratch, and how to translate this into continuation passing style thing with global variables and a stack and on Scratch. So, and some kids are learning this, but my impression is those are older kids who are nerds already and who probably don't even need to learn these things. They're just doing it for fun. So you're right about the sharing. I mean, that's kind of at the heart of constructionism, is really the interaction with others. It's author's pride, and it's also getting the feedback, not just from the computer, but from your peers. And obviously, Scratch is amazingly good at that. I mean, I love Scratch myself. I mean, I worked on Scratch, and I still use it, every other day. I just love it. So yes, we can share projects the way I've shown you, package them as application. You can also share them on our clouds. You get a URL that you can paste into Twitter, which just isn't what people need. So there's obviously work to be done on the social aspect. Absolutely. Even right.
Thank you. Thank you very much.
Thank you.
Merci. On va passer maintenant.